Hopefully you guys can all hear me now. Thank you so much, Teo, for the introduction. I'm a PhD student from the University of St. Andrews. I'm working remotely in Canada, and I'm working with David Borchers, Michael Papatamas, Rachel Fuster, and Ben Stevenson is very involved. So today I'm going to talk about latent ID, acoustic, spatial capture, recapture. And this is going to be a talk about what you can do if you were tuning in for Rachel's talk earlier. We're going to assume here that you can match the calls to the microphones and group syllables. So we have that added information that kind of fits into a more traditional spatial capture recapture framework. And so if you guys are familiar somewhat, our motivating problem here is that kind of what we see from analyzing acoustic spatial capture recapture data is that we get a rough idea where the animal calls came from, but we don't know who is who. And so we see things like this, where the calls are bouncing around. And we're like, okay, well, if they're kind of from the same place, maybe they're the same animal. And this is the kind of classic assumption that we're starting to make with a lot of latent ID models, is that the spatial information gives you a clue about who is who in the population. And so we want to develop a model that uses that, but obviously we don't know exactly where these animals are calling from. And so we need to develop a process to kind of match calls to their animals. And so that's what this talk is about. And so to me, the solution is conceptualizing this as a mixture model. And so if you assume that you know where the animals are and who they are, like in this picture below, and then you hear them on two microphones, then it's likely it's one of these two animals. Maybe it's this one. It's certainly not this. And that's fairly easy to write down as a mixture model. And that's what we're going to try to do in this talk. And so again, every time you hear a different capture, see a different capture history, it kind of informs who is who, and that, can hopefully give you information about matching pairs. And so traditional ASCR models, just the observation process, which is calls coming from locations. And so we have that kind of already worked out. We need a call production process about how the calls are produced from the animal. And we need an animal production process. So where are these animals? What are their attributes? So a quick review of ASCR. You have an observed call that's emitted from a certain location, and it's recaptured across a grid of J microphones or traps. So this is very similar to the spatial capture recapture. And what we're going to work with is the conditional likelihood. So calls must be detected on at least one microphone. Each microphone records the time of arrival of the call, and that information triangulates the animal position. So we're going to kind of assume that we're going to be able to get this, and it allows us to kind of go into continuous time models. So it gives us information on when the call was produced, and that's going to be quite critical later on. Then there's other information you can include. Signal strength gives you an estimate about distance as the signal strength decays through space. And you could maybe say that the call frequency matches to a specific animal if each animal calls somewhat uniquely. For Kiwi, you can determine sex from the call type. So that would tell you that at least this call came from a male or a female animal. So again, those types of things are useful for clustering, and we, we'll build a model that can kind of incorporate that information. So call production, in a time period T, each animal might make N calls in that period. So that's what's happening. And these observed calls are thinned by detection. So we're not necessarily going to hear every call, but we'll hear more of the calls that are closer to the microphones than further away. And if we assume that those N's are Poisson, then the inter-arrival times are exponential. And we can use that inter-arrival time to link the observed calls to their animals at that location. Okay, so right now for the animal, we'll assume that the animal calls from fixed locations through the study period, but we can kind of relax that assumption later. But right now, that's the strongest spatial clustering we can do. And what we're saying is if animals share the same call location, then they must be the same animal. The locations are uniform across the study area. That's a common assumption, but and we'll start there again because we're developing a new model here. And we're going to assume that the animals behave independently and that they have this additional information about themselves that may or may not be known, and but they, male or female, unique calling types, or anything else that the biologist might think is unique to an animal that we can get from the acoustic survey. So as a mixture model, we think of the observed call as a, it's coming from this continuous spatial temporal process where we have these points in space that are making noise, and we know when this noise was called. So if we condition on the calls coming from all the other animals that have been heard, then we can write down the likelihood of this call being heard as a mixture model. And we can use that inter-arrival time to say, well, it belongs to, if the call was heard very late in the survey, it was either part of a really big group in the center, or it must be really far away for it to be by itself, right? For it to be the first time you hear it. And so that inter-arrival time gives us some information, but again, that's paired with the information we already have about space, which is the recapture across the grid, the time of arrival, and potentially signal strength. And then the animal location that this is all conditional on gives us the information for that cluster group about the whole process. So where it is, its sex, et cetera, but for this talk, we're just gonna stick with plain location. So that's the mixture model, if you can picture it. I'm trying to avoid too many equations and just kind of give you guys the basic idea here. So I've described a great mixture model if we know where the animals are and how many there are, but we don't know that. We just kind of know that there must be at least as many observed animals as observed calls. And so we can't have more animals calling than calls that we observe, but that doesn't really constrain it that much. And so what we've seen a lot of recently is this idea with SPIM, or unmarked SCR, and these ideas that use data augmentation and just sample through all possible partitions of the data. But the nice thing here is that we're kind of building a model that links observations to the animal on the individual level, so that it's a mixture. And so we can kind of use some other theories or some other methods that might work a little bit faster. So here we're going to assume an infinite number of potential animals, and we're going to treat it as an infinite mixture model. And what's cool here, or the reason to do it, is that we never assume that there's actually infinite animals. We just have this, we just use this for computational purposes. So what we can do here is build this model using the theory from a Dirichlet process mixture model. And I'm not going to go into that. I just finally realized that this isn't a Dirichlet process mixture model because I'm parametrically describing the number of calls per animal. But the Chinese restaurant process will allow us to sample from these unobserved processes, and then we can fit all the observed process stuff conditional on that. And so it should be fairly straightforward. The Chinese restaurant process is really neat. You just assume that everybody's already sitting down, and the table tells you where the animal is or any other animal-specific partition information. And then you just march that call to each table and say, oh, do I belong here? And if not, and if you can sample from the posterior predictive distribution, then you can say, oh, what's the probability I just go to my own table? And this just really quickly creates partitions that are proportional to the posterior distribution. So this is really cool and a really fast way to sample partitions of the data without trying to have to sample a bunch of empty boxes. And so we've done it on some simulated data. Here's 95 calls, which is the example I showed on the first slide. And there's 10 animals. Their call rate is 0.1 per second. And we ran the study for 100 seconds. We use a hazard half normal detection function and time of arrival uncertainty of 0.02. And the red line, blue line, and black line are all overlapping. The red line's the true. We're pretty much bang on it with the black. Those are the posterior means of the detection function. And the blue is if we knew ID, what the MLE would have been. So we're all the detection stuff agrees, and that's fantastic. So I've still got a little work to do working on my samplers here. I only just got this running last week, but what you can see is that we're doing really well. Ignore my sigma TOA. I think there's a little error in there. But what's really cool here is we're getting exactly the same posterior estimate of the call rate lambda as the MLE of the known ID, and we still have nice coverage of the true call rate. So that's really neat, and that's really cool to see. And then what we see is that we're actually recovering the number of animals really well. If we're getting call rate, then we should probably be able to estimate the number of observed animals. And you see that we're actually partitioning the data really well here. And so we're getting that between 8 and 10 or 12 animals, and there were 10, and we're pretty much bang on there. So that's really good to see. And I only got this code working last week. So when I'm started seeing it consistently, I got pretty stoked. Yeah, so I made some tweaks to the Chinese restaurant process theoretically that make it no longer a dishly processed mixture model. And I just need to do a bit of math there to prove that this is still sampling correctly. And then I've worked out all the theory for adding all these extra attributes for clustering. I just haven't written that out yet, so into code. So I'll be doing that next. So yeah, just want to thank all my funders and stuff like that. And thank you so much for sticking around for the talk.
Okay, thank you very much, Paul. Thanks, very interesting talk. So there's not a question, but a comment from Murray on the chat, who's saying that often asymmetrical mixture models work well in simulations, but for field data, the call rate estimates are very sensitive to the arbitrary acoustic detection threshold. Do you have thoughts about this?
I mean, I think Murray's probably right. And I think what's cool here is that, we're starting right now with an exponential arrival time model here, but that doesn't have to be what it is. And so if there's any structure in the data, we can actually build this up to include all of that information and kind of use that to maybe create more realistic models. Again, animals are probably going to move just small amounts during the study period, even if we have nice clusterings of calls. So we're going to need to incorporate that. And yeah, we want to this is just the starting point. Yeah, but so far it's been pretty successful.
Okay, great. There's another question from Beth, who's asking what effect would you expect to see for species that might be in pairs or groups?
Yeah, so again, it's all about clustering as far as the information we have. So a lot of times you'll have paired callers of like kiwi, male and female, that duet together, and you can figure out that they're different because they're male and female, and we can incorporate that, and that's no problem. But if they're gonna sit right next to each other, then you're gonna need additional information to tease them apart. And so this just assuming that if they're coming from the same location, it's the same animal, is just not gonna work. And so if this is like a saturated in density, area, and you don't have ID, you can't really recover ID without more information. There's no silver bullet. And so I think, yeah, you just have to be realistic that you're kind of hoping, that this might work for territorial animals or for animals that show specific clusters across the capture array.